Welcome to today's video, 5 top tips on dynamic equilibrium. So my first top tip is making sure that we understand what is meant by a reaction at dynamic equilibrium. So reactions can be reversible, meaning reactants can be turned into products and products can be turned back into reactants again, but that doesn't necessarily mean that that reversible reaction will get to dynamic equilibrium. First of all, we need to be carrying that out in a closed system so that no reactants, products or energy can enter or leave the vessel. And then to be at dynamic equilibrium, we need to have two features present. One is that the rate of the forward reaction and the rate of the backward reaction are the same. Two, that means that the concentration of the reactants and products stays constant. Now, we're not going to say that the concentration of reactants and products stays the same, because that would suggest that we end up with a 50-50 ratio of our reactants to products, and that is a potential outcome, but it's not always going to be the case. Now, the reason why I've got my pens out here in front of me is I'm going to try and show, using a really simple analogy, how a reaction may start and how it might approach dynamic equilibrium, and then what that would look like when the reaction has gotten to dynamic equilibrium. So analogies, I think, are really good for this because it's a really abstract concept to be thinking about. And the other analogy that I quite like is a person trying to run up a downward escalator. So the person starts at the bottom and they represent the forward reaction, and they're trying to move upwards towards the top of the escalator. And the escalator that's moving downwards represents the reverse reaction. Now, initially the person running will have momentum and they will make it so far up the escalator, but then there will become a point where the person gets a bit tired, and then their speed is matched exactly by the speed of the escalator bringing them down. So they will still be moving and the escalator will still be moving, but the person will be staying on the spot, as it were. And that would be dynamic equilibrium, because the person isn't moving from their position on the escalator, and their speed and the speed of the escalator, i.e. the speed of the forward and the backward reactions, are matched. They are equal, they are the same. So that's one analogy we can use. I like the pen analogy because this is representing my reactants. Now, we don't have to start with the reactants if we have a reversible reaction, but we do tend to. So in the beginning of any reaction, only the forward reaction is going to be taking place because there's currently no products in this pile over here. So in my very basic reaction, I am going to take the lid off one of the pens, and then the product is the pens with their lids off. So that represented the forward reaction, and I'm now going to do that forward reaction again. And now I'm going to do it again. And there will become a point with our reversible reaction, if it's being done in a closed system, whereby the backward reaction kicks in. Now, when the backward reaction starts to kick in, the backwards and the forwards will be occurring at the same time. So forgive me because this is going to be a bit tricky to demonstrate on my own. But now you need to imagine that we've got to this point, and now the reverse reaction is going to start occurring. So the lids are going to go back on in the reverse reaction to put them back in this pile over here. But at the same time, the forward reaction is still occurring, which is taking the lids off the pens to make our products. Now, if I had two people, this would be easier, because what I would be doing is, for every time that happened and a lid got put back onto the pen, the second person would take a new lid off a new pen to represent the forward reaction. And then that process would continue with those two people, one putting the lids on the pens and one taking the lids off the pens at the same speed. Now, what we can hopefully still see in my version is that every time I put a pen with a lid on, I'm taking a lid off another pen. And the amount that I have in this pile representing my reactants is staying constant. There is now always two pens here, and there are always 3 pens and 3 lids on this side representing my products. So every single time I do this and a reverse reaction occurs, a forward reaction also occurs, and that keeps the amount or the concentration of reactants and products constant. Now you'll notice that I don't have the same number of pens in each pile. as I said, that is a possibility. We can have 50% reactants and 50% products, but actually we can range from anything that is nearly nothing in the reactants to nearly all products, and vice versa. So in mine, I've got 2/5 reactants, which is 40%, and 3/5 products, which is 60%. And we can range anywhere, like I say, from nearly 0 to 100 to nearly 100 to 0. Now, ideally, anytime we do a chemical reaction, we want to make more product. So you might get to a position of equilibrium like this, 40% reactants and 60% products, and think, yeah, that's not bad. But how can we increase that 60%? This is where we need to think about what changes we can make to temperature or pressure or concentration to enable us to shift the position of equilibrium so that we have more pens in the product pile, or if we're thinking back to the man on the escalator, so that the man gets higher up the escalator before his speed and the escalator speed are matched. That's what we're now trying to do so that we can get more product. And that will lead me on to tips 2, 3, 4 and 5. So my second top tip is just having an understanding of the fact that we can have a reversible reaction at dynamic equilibrium, and then if we potentially want to change the temperature, the pressure, the concentration to favour a forward reaction to generate more product, we will eventually get to a new position of dynamic equilibrium, but during that change we cannot be at dynamic equilibrium anymore. Because one of the features of dynamic equilibrium is that the rate of the forward reaction and the rate of the backward reaction are the same. And if we are purposely trying to favour the forward reaction to increase the yield of product, then we will be having more of the forward reaction occurring and less of the backward reaction by comparison occurring. When we get to the new position of dynamic equilibrium, that can be re-established in that the rate of the forward and the backward reaction will then stay the same, and that will keep the concentration of reactants and products at that point the same in their new proportions. So in this image you can see that we may start with a 40-60 ratio, but what we might want to change that to is a 20-80 ratio. In the process of making that change, the forward reaction will occur more than the backwards reaction, so no dynamic equilibrium there, but we will then get to a point where we are back at dynamic equilibrium. Both reactions are occurring at the same rate. We have our new fixed concentrations of reactants and products, which then themselves remain constant. Here are tips 3, 4 and 5. Tip 3, I'm going to talk about annotations that we can make onto our exam question. Tip 4 is the key information that we have to unfortunately just sit and learn so that we can draw that from our memory when we come to answering questions on how the position of equilibrium is going to shift. And then tip 5 is linked with exam structure. So once you have worked out how the position of equilibrium is going to move, tip 5 should then give you all of the information you need to be able to structure that answer in a way that is going to get you marks in your exam. So I'm a firm believer that the more information that you can get out of your brain and onto the paper in an exam situation, the better. So once I've worked out what the question is asking me about, is it temperature, is it pressure, is it concentration, or it might be a multiple choice question which is alluding to each of these are the annotations that I would be looking to make straight away. So with regards to temperature, we have to be told some sort of information that allows us to know whether the forward reaction is exothermic or endothermic. That's not something that we can assume is the same for every reversible reaction at dynamic equilibrium. So in this case, we've been told that the enthalpy change, delta H, is negative. If you are given that information, that tells you that the forwards reaction is exothermic. It's always the forward reaction, and because it's negative, that means it's exothermic. So then I would be adding on, as I have done here, forward is exo, backwards is endo. And that then means that I'm just not holding that information in my brain when I'm then thinking about the next part to come. For pressure, we need to be considering how many moles of gas we have on each side of our equation. So it's just a simple counting exercise. In this example, I've got 2 moles of gas in my reactants. I've got 1 mole of A and 1 mole of B, which totals 2. And then on the product side, I've only got 1 mole of C. So we need to know how many moles of gas we've got in total for our reactants and the same in total for our products. And again, I would write those numbers on. You can just put a big number 2 at the top and a big number 1 at the top, or whatever the numbers might be, whatever works for you. But again, it's just less information to be holding in your brain. Concentration is a bit trickier to know what may be potentially helpful, but again, rather than having the information in a big chunk of text in the question, I like to have the information shorthand around the information that's useful. So for concentration, what I would be doing is just identifying which substance is having its concentration changed. Is it a reactant? Is it the product? And is that concentration being increased or decreased? So if C's concentration is decreasing, I might write decreasing concentration underneath C. If B's was increasing, I would write increasing concentration underneath B. Again, visually, I find that more helpful than having it written just in the question. And again, it's getting that information out of my brain to enable me to then go on to the next part. Tip 4 is the next part. So what key information do we need to know in order to work out how the position of equilibrium is going to shift? So we need to know that for temperature, anytime the temperature is increased, the endothermic reaction will always be favoured. And anytime the temperature is decreased, the exothermic reaction will be favoured. Now, this is all down to Le Chatelier's principle and him saying that the system will always work to oppose any changes imposed upon it. So if I increase the temperature, the reason why the endothermic reaction is favoured is because that is the one that is going to absorb the additional heat that I am adding, and that is going to take the system back to the status quo, what it was before. And again, on the theme of analogies, for temperature, I like to think about it's a winter's day and potentially your parents have opened all the windows in your house. You're not going to just sit there and allow yourself to get cold. You are going to take action to oppose that change, either closing your own bedroom windows or getting into bed under your duvet or blankets or extra layers or something. That is you doing something to oppose the change, and reactions at dynamic equilibrium will do the same. So decreasing the temperature favours the exothermic reaction because that's the one that's going to release heat back out again to raise that temperature back up to what it was before. So that's the key learning we have to know for temperature, and we've just got to learn that, and that should be something that you can draw upon really quickly then in the exam. For pressure, it's all about the side with either the fewer moles or more moles of gas, and increasing the pressure favours the side with fewer moles of gas, and decreasing the pressure favours the side with more moles of gas. And again, that is to oppose the change that I am imposing onto the system. So if I'm increasing the pressure, favouring the side with fewer moles of gas will mean there are fewer collisions of those gas particles with the sides of the container, and that will help to bring the pressure down again. And the converse is true if I decrease the pressure. Favouring the side with more moles of gas will result in there being more collisions with the side of the container, which will slowly raise the pressure again. Now, concentration is a bit trickier because there's kind of 4 different things that we could do. We can increase the concentration of either the reactants or the products, or we could decrease the concentration of either the reactants or the products. So I've tried to word it so there's only 2 scenarios here. So anytime we increase the concentration of something in my equation, it's always going to favour the reaction that is going to react away the extra that is added. And anytime I am decreasing the concentration, that will always favour the reaction that is going to replace what's being taken away. If you learn those 6 points, then any equilibrium question where it talks about changes in temperature, pressure and concentration, you should be able to work out which way the position of equilibrium is going to shift. Then tip 5 comes in, which is how you're going to structure that in your exam answer. So there are 3 non-negotiable things that you have to mention in your exam answer, and potentially there may be a 4th thing that might be relevant or necessary for you to include as well. I always write my exam answers for equilibrium questions in this way. I don't try and change the way I structure any of my answers at any point. I always follow this same structure and I'll use the same sentences, just changing very few words as I go along. So the first thing I would always say is, which way does the position of equilibrium shift? Is it shifting to the left towards the reactants, or is it shifting to the right towards the products? The second thing that I will mention is what is being favoured by that change in the position of equilibrium occurring. So is it favouring the exothermic reaction, or is it favouring the side with more moles of gas, or is it favouring the reaction that's going to use up and react away the extra concentration that's been added, whatever it might be. And then the third thing that you have to mention is what is being opposed by that happening. Now, when you're talking about what is being opposed, do not just say that this is happening to oppose the change. Instead of the change, specify what the change is. So is it opposing the increase in temperature, or is it opposing the decreased concentration of X, Y, Z? And then what you might need to also mention is how does that have an effect on the yield of the substance that it might be talking about. So it might say, talk about how changing the temperature affects the yield of whatever the product is in that particular reaction. And then obviously you would also have to comment on that too. So those are the things that I would be mentioning. So for example, my answer might say, the yield of product will be increased in this reaction because the position of equilibrium is going to shift to the right. This is because increasing the pressure favours the side with fewer moles of gas, and this happens to oppose the increase in pressure. Thank you so much for watching. I really hope you found it helpful.